Hello everyone, in this video I'm going to talk about gear ratio. So we use gearing to increase the torque, decrease the speed, or the other way around. So as we previously talked, we know the power is T omega, and then if two gears are in contact, usually we are increasing the torque, decreasing the speed, but there are some applications that you want higher speed as well. So let's say we have two gears in contact. I'm gonna call them gear A and gear B. They have radius RA and RB. So if gear A is rotating clockwise with a speed of omega A, gear B would be counterclockwise, and that would be omega B. At the point of contact, the velocity is the same. I'm gonna call it VC. Do you know why the velocity is constant at the point of contact, or not necessarily constant if the gears are rotating, but the same for both gears, because we don't have any slipping or sliding, is absolute rolling. If I use the information for gear A to calculate the velocity at point of contact, that would be RA omega A, and then for gear B, RB omega B. So if I set these equal, I will get omega B over omega A would be RA over RB. That means that the velocities are inversely proportional to the radius or to the diameters. And we call this ratio velocity ratio, VA. That's called the velocity ratio. So if I'm going from a small gear, gear A, to a larger gear, gear B, so if RB is higher, you can see that the higher value would be in the denominator. So this fraction is less than 1. That means that the speed is reducing. And when we have a reduction in speed, we have an increase in torque. So the smaller gear always rotates faster, and that's something that you need to remember. Also, if I want to relate the speed to the number of teeth, I already know the diametral pitch, which is defined as N over D. Therefore, the diameter would be the number of teeth over diametral pitch, or if I want to write it in terms of the radius, that would be 2p. And the diametral pitch is just determines for us how fine or coarse our tooth is. And the diametral pitch would be the same whether we are using for gear A and B. For two gears in contact, one of them cannot be finer than the other one. So they need to have the same diametral pitch, or their number of teeth over diameter ratio should be the same. So if I replace this R into the equation here, I get omega B over omega A. Instead of RA, I write NA, 2 over diametral pitch, and MB over 2 diametral pitch as well. These two are the same, so I get NA over MB. And also we knew that's DA or RA over RB as well. So we have this ratio. The rotational speed of each gear is inversely proportional to the diameter, to the radius, and also to number of teeth. And again, this is the velocity ratio that we talk about. Let's look at the torque relation and see how the torque is changing. So if you have two gears again, I'm going to draw the two gears. And here I'm just going to draw one tooth out of all of them for the gears. So if this one is rotating clockwise, is pushing the other gear. This gear, when this tooth comes into contact to the other one, is pushing this downward. And that if I only draw the tangential component, that would be force F. Then there would be a reaction force acting on this gear, gear A. So that would be force F. And we know this is action and reaction. That's why the two forces are the same. So if this one is clockwise, this one is going to be counterclockwise. And you can see now why, if one of them is clockwise, the other gear should be counterclockwise. Because when this tooth pushes this gear down, it pushes it to rotate in the opposite direction. So here again, the radius are RA and RB. If I want to find the torque for each case, TA would be FRA and TB FRB. Therefore, F is TA over RA. And if I write it as function of STBRB, if I set these two equal to each other, so TB over TA would be RB over RA. And we call this mechanical advantage, because we want to see our torque, the output torque versus our input torque. And if this value is more than 1, then we got an advantage using gear system. And this is directly proportional to the size of our gears, to the radius or to the diameter of our gear. And from the previous slides, we know that's MB over NA. So if you're going from a smaller gear to a larger gear, your speed is decreasing, but your torque is increasing. And depending on application, you would decide whether you're interested in increasing your speed or decreasing speed. As I said before, in most cases, you are trying to increase the torque. Increasing speed, high speed is easy to achieve. If you have an electric motor or if you have an engine, for example, manual transmission, you have reductions. You're increasing the torque for gear 1, gear 2, gear 3, gear 4 is directly connected. The input and output, and gear 5, you're kind of increasing the speed. But in most cases, you have reduction. So this is a mechanical advantage. If I write my speed towards the end, which was the only one that was inversely proportional, I get this long ratio. Here are the relation in a 100% efficiency case. Then the input power is the same as the output power. Torque times omega gives us the power. So we have a trade-off between torque and RPM. So omega in, omega out, R out, R in, output and input. That's the mechanical advantage, and that's the velocity ratio. In a lot of problem, you want to know what is the mechanical advantage and what is the velocity ratio that you have. So remember these two fractions. And here you can see if one of them is here is counterclockwise, so the other one would be clockwise. And when they're rotating here, the speed is going to be the same at the point of contact, and the forces would be the same. And we call this a conjugate action when we have a rolling at the point of contact. And when we have rolling, that means that the velocity would be the same. There is no slipping, and therefore the angular velocity would be inversely proportional to the radii. And in gearing, we can assume conjugate action, and that's a good assumption with minimal error for most cases. Now we're going to look at some of the problems. So here we have a 17-tooth spare pinion. So pinion means a smaller gear. It doesn't mean it's a driver. we call the smaller gear pinion. It could be a driver or it could be a driven gear. Has a diametral pitch of 8 teeth per inch. So if you look at the units, you can tell the equation for this. Runs at 1120 RPM and drive the gear at a speed of 544. Yeah, that's we expect. The speed is reduced from 1120 to 544. Find the number of teeth on the gear and the theoretical center to center distance. So we have a pinion with 17 teeth. Diametral pitch is 8 teeth per inch. The RPM of the pinion 1120. The RPM of the gear is 544. If you look at the gear ratio, you can see that we have the RPM of the pinion, the RPM of the gear. We have the number of teeth for the pinion, sorry. That's what we want to find. We have this, then we can find the number of teeth on the gear. That would be 35 teeth. So it's higher than the pinion. So that's one way to check it. It's a bigger gear of the two. The problem is asking for center to center distance. That means that we need to find the diameter. So if we have the diametral pitch, you know the equation for the diametral pitch is n over d, and diametral pitch would be the same for both cases, whether it's pinion or whether it's gear. Two gears in contact in mesh, they need to have the same diametral pitch, circular pitch, module, and all the gear features have to be the same. So based on this, I can find the diameter of gear and pinion. The diameter of the pinion would be 2.125 inch. The diameter of the gear would be 4.37. And also, because now I have the diameter of the pinion, I could go back here and based on the gear ratio, find the diameter of the gear as well. So if you do that, of course, you get the same answer. Center to center distance is just the addition of the two radius. So here we have the diameter, that's why we divided by 2. So that's a center to center distance. And these are pitch diameter. So those are not addendum or dedendum. And that's how you place the two gears apart from each other. The center to center distance, we deal with the pitch diameter. Let's look at another problem. A 15-tooth spare pinion has a module of 3 millimeter and runs at a speed of 1600 RPM. The driven gear has 60 teeth. So when you look at it, you have 60 here, you have 15. So the ratio is 4:1. Find the speed of the driven gear, the circular pitch, the theoretical center to center distance. So we have the number of teeth for the pinion, we have the module, we have the RPM, you have the number of teeth on the gear. And when you look at these 15 to 60, your gear is 4 times more, so your speed should be 4 times less. And we have the module, so that's the SI unit. So the number of the RPM for the gear would be 400, as we expected. We have a reduction of 4:1. We have the circular pitch. That's the equation for circular pitch. Pi d over n, and that's the same for the gear and pinion because they are in mesh. And d over n is module, so that's pi module if you want to find the circular pitch, and the module is given to us. So the circular pitch is 9.42. So we have everything. We want to find the center to center distance, which means that we need to find the diameter. We have the number of teeth, and we have the module. So we can find the diameter. The module is simply d over n. So the diameter of the gear, the diameter of the pinion, therefore the center to center distance would be the radius, addition of the radius, or you find the diameter and divide it by 2. So that would be 112.5 millimeters. So that's how far you need to place the two gears from each other. So if these are the pitch radius, that's how far you need to place them. Radius of one plus radius of the other one will give you the center to center distance. The other problem is, again, we have a module of 6 millimeter, a velocity ratio of 4. So here is, we have the velocity ratio. The pinion has 16 teeth. Find the number of teeth on the driven gear, the pitch diameter, and the theoretical center to center distance. So we have the module, we have the velocity ratio, we have the velocity ratio is 4, so the pinion is the one that drives the fastest. So that's the velocity ratio that we have. If we have the number of teeth on the pinion, then we can find the speed of the gear and so forth, and the number of teeth on the gear. 64, the diameter of the gear, if you want to find the center to center distance, and the diameter of the pinion. Again, the module is the same for both, so I can find center to center distance. Let's look at the fourth problem. So here, a gear set, we have 16 tooth pinion driving a 40 tooth, so a little bit more than 2 the gear ratio. The diametral pitch is given to us 2. The addendum and dedendum are 1 over diametral pitch and 1.25 diametral pitch. So we showed one by A, the other one by B, and we called, okay, it doesn't ask for the clearance, but the clearance is B minus A. And these are the equation that we have, and that's true for almost all gears, not just this problem. The gears are cut using a pressure angle of 20 degrees. So that's pressure angle 20. Show it by phi. That tells us the angle that our force is making with respect to the tangential component and the radial component, if you want to find FR and FT. Compute the circular pitch, the center distance, and the radius of the base circle. So the only additional parameter that we need to find here, compared to the other problems, is the base circle. Part B is interesting. We're going to go and read part B after we are done with part A. So here we have the circular pitch. If you have the diametral pitch, it's just pi over diametral pitch. You find the circular pitch, and you can find the diameter of pinion, diameter of the gear, center to center distance, and then the pressure angle, and then the base radius, which is the radius times cosine of the pressure angle. RB is R cosine phi. And the base radius tells us, or the base circle tells us, the depth of penetration, how far the two gears would get engaged to each other, and then how far the tooth of one gear go into the tooth of the other gear. That's the physical meaning of the base circle and the base radius. Is if this is our gear, so the top part is the addendum, the bottom part is the dedendum. Somewhere here would be the pitch radius, and base radius would be even further down, somewhere between the pitch radius and the dedendum. So you can find the base radius for both. As you can see, it's less than the radius of the pitch radius, which is 4 and 10. The second part of the problem, let's go read part B. In mounting these gears, the center distance was incorrectly made 1/4 of an inch larger. So when we were placing the two gears, instead of placing them exactly correctly with the correct tolerance, we moved them a little bit apart. We want to find what happens to the pressure angle or the pitch circle diameters. So if we place them further apart, that means that we have a new center to center distance. It's no longer 14, but 14 plus 1/4 of an inch, 14.250. Also, the velocity ratio is not changing because the number of teeth is not changing, so the velocity ratio is the same. So we can find the new pitch diameters. So we can find the new pitch diameters. The base diameters or the base radius are the same because that's the property of your gear. You can find the new pressure angle. which the pressure angle gets a little bit higher. So we do not like higher pressure angle. Again, if you have the force acting on your gear, that's the pressure angle. And if you want to find the tangential component, that would be F cosine phi. So the lower our pressure angle is, the higher the cosine and the higher the tangential component. And that's the component that we are interested in. Problem 5 is the one that you need to solve. Is a motor rotating at 500 RPM, needs to drive a shaft at 1250. So that means that we are actually increasing the speed here from 500 to 250. We want a gearing system with a diametral pitch of 2 teeth per inch, pressure angle 20 degrees, standard pressure angle. You want to find the gear ratio, the pitch diameter, number of teeth, circular pitch, center to center, addendum, dedendum, clearance, basically everything that we have learned so far. And we want to find the speed of contact. So we are talking about the angular speed, right? R omega. Or if you have n, so that would be 2 pi Rn. So we have the RPM of the pinion, the RPM of the gear. We have the number of teeth on the pinion. Based on this, we can find the number of teeth on the gear as well. We have the diametral pitch, pressure angle. We want to find the diameter of the pinion and the gear, the number of teeth on the gear, the circular pitch, center to center distance, and the base radius. When we have the pressure angle, we can find the base diameters or the base radius. A and B, addendum and dedendum respectively. C, clearance, which is just the difference between the two, B minus A. The velocity, again, this is the linear velocity, or omega. And here is showing you just a schematic. We have 500 RPM, we are going to 1250. Of course, you have to go from a larger gear to a smaller gear because you want to increase the speed, and consequently the torque is gonna decrease.